Okay, lecture 24. Still on zero knowledge systems. I promised I'd get back to using zero knowledge as a system of identification. And the simple algorithm that doesn't have a bunch of fixes is the Schnorr identification algorithm. It's the basis behind SRP6A, the secure remote password. Secure remote password takes care of a couple edge cases and makes things better, but to understand SRP, you've really got to understand this algorithm. This is the algorithm without mitigation of special cases. You can go searching for SRP6A. There's a nice Wikipedia article on it. There are standards. Do be aware of the fact that the example Python code in the Wikipedia page and also in the standard, there is one section in there that has some type conversion errors in it. So it is an example, but it only works when talking to itself. It does not work correctly in a reliable fashion when talking to other systems using that authentication. Do be aware that the Python code in the example and in the standard has a routine that is 4 lines long that has 5 type conversion errors in it. So it still has some problems that need to be worked out, even though it's in the standard. But I want to show you the basic algorithm. Now, the other detail that I want to point out real quick is in this first article here that goes through the algorithm in some detail on the web. You're really looking for page 40 down here at the bottom of the page, not the page numbers over here. A walkthrough of the example in the paper. There's a second one there that does the same algorithm but actually has a nice walkthrough. And I want to take a detailed tour of it, but before we get off on that detailed tour, I want to take a tiny detour in using QR codes or RFIDs for authentication. There's always people that want to get these things to work in this fashion, and QR codes are static, so you're not going to get much processing power out of a piece of paper or an image. But things like NFC codes are either static or can have a processor in it that does a little bit, but you have to put in perspective how little that little bit is. Basically, NFC can return a text string, just like a QR code if you decode it as a text string. So you can store pretty much anything in these up to the size limits that you can get away with. NFC is between 84 and 1084 characters. QR codes, it depends on how big the image is and how much redundancy you want in the QR code. The greater the level of redundancy, the bigger the image has to be relative to the original text. So the shorter you make it, the better off you are. But in any case, you think about something like NFC. You have a transmitter from something like a phone that you want to transmit, and it receives a signal on the NFC chip or the NFC RFID, however you want to call that. It uses its antenna to power its processing, which means you have a tremendous loss of power from the transmitter, which, if it's something like a phone, didn't have a lot of power to start off with. This is not a 10,000 watt radio station. And so you get down to the fact that it has very little power, and then you're expecting it to turn around and do some sort of a computation on this tiny bit of power, and then turn around and transmit back a result. So its transmit back is even lower power, and that doesn't leave you a lot of room for doing much computation. It's pretty thin. In fact, it may be so thin that you can't do anything complex. I mean, the ideal thing would be if there was some way that you could implement some sort of zero knowledge proof right inside the NFC, but it's not got a lot of electricity there to manage to compute that. And generally speaking, these computations are complex and difficult. That's why they prove their zero knowledge stuff. So the alternative to that is you have your QR code or your RFID basically refer you to a second factor of authentication. The second factor of authentication is something like a phone, where you can turn around and use that to do the complex computation on the proof of authenticity or the two-factor or something like TOTP, time-based one-time key that proves that the person is in possession of the phone. That's used like Duo, that's what they're doing. So these things can be made to use as authenticators, provided that you can actually just go, okay, this thing, what it does is it stores a string. I'm going to make the string into an URL, and I'm going to take the application off to some page. All right, now at that page, I'm going to do the second pass and do some serious authentication. I wanted to do that before we get into zero knowledge, because zero knowledge can still be used on things like tags and RFIDs, but you've got to have some outside capabilities to make it work. I've got a piece of code here that we're going to walk through this algorithm for the Schnorr identification protocol. You've got the original stuff up here, or this isn't the original, this isn't Schnorr's paper, but it goes through it and it gives you some sample values that if you use those values, they're all walked through, and I have implemented this code to use those values. Now, the realistic values that people actually use for this are much bigger than that, okay? They are actually quite large. For instance, here's the value for SRP6A and the standard values for the prime number. And this in hexadecimal is the prime number. So our prime number at 5 digits is teensy compared to what you actually use in the real world. Now, the nice thing about having an example with little tiny numbers is we can actually calculate these out on a calculator and see that our algorithm works. The second thing I want to point out in terms of calculating these out is that by doing them with some standard values, we can actually eliminate the random number generation, and we can do this repeated. So when we're testing, we really don't want random numbers, because that way, if you have random numbers, every test comes out different, and that's kind of the point of the security, but it also makes it impossible for us to repeat tests. So in here, when I've got some sort of thing that returns some new int, not there, but right here, where we are going to have a random number generated. There's one in here someplace. There's 2 places where we generate random numbers. You know, what I do when I'm testing it, and I've supplied 2 pieces of code. There's one of them that is the non-random number version, and then there's the one we're going to walk through that has the random numbers. The non-random number version is for testing, so that you can actually work out the code and get it to work right. But I want to run through how this works relative to the algorithm and take a look at the math and the numbers so that you can actually see how the identification process works. Built into the way that I'm looking at this is the fact that you're going to have multiple calls coming into a server. And rather than just storing these things in memory and trying to match them up, what we do is we have a tiny little database. My tiny little database is not written out, but my tiny little database is this data structure in memory. And when I want values saved for the next call, they have to go in the database. And the values that I want saved are these: V, E, Y, and X. And by doing it this way, this means that you could split it up into a set of separate calls. When I have implemented this for SRP6A, I've actually implemented it where the database was a Redis in-memory database that allowed me to have multiple servers running and each one receive calls independently so that you don't have dependencies between the calls. You're not trying to trace one RESTful call through to the next. It just stores the stuff, the intermediary results, as it's going through the multiple calls. Now, the fact that there are multiple calls is one of those things that you have to be aware of in these kind of authentication systems. It's going to take more than one call to your server to get the authentication done. And that's one of the disadvantages of all of these. Most of them, like SRP6A, require 3 calls. I think this one only requires 2, but you don't quite get all the same information as in SRP6A. This is a little bit simpler. There are ways to make the SRP6A get it done in just 2, but that means that the server has authenticated that the client is the correct client, but the client hasn't authenticated that the server is the correct server. So you lose some capabilities if you decrease the number of calls. So this little section that I highlighted is my database. All it is a map from a string to this record, and I just allocate memory for it. The string is going to be the username. So these are the things that I can store in the database. Okay? I have, at the beginning of the code, something to set up a random seed so my random number changes on a regular basis. It doesn't repeat. If you don't include that in Go, then you consistently get the same random number generated every single time you call this random number generator. Now, the random number generator I'm using is not the cryptographic random number generator. This is just the give me a number, we're going to do this computation with it. This chunk of code tends to be a little bit harder to read because everything is done assuming we're doing calculations on big integers. You looked at the size of the actual numbers, you're going to do big integers, you're not going to do just, 64-bit ints. This would be really short if we could do 64-bit ints, but the realistic version is all thousands of digits long calculations, or at least hundreds of digits long. So I start off with P, which is the password. And you don't actually use a password. What you do is you take the person's password on the client side and you hash it into a number. Because the hash of the password, probably with some other kind of salt added to it, is the actual value that you're going to use to generate a thing called a verifier. And this first piece here between lines 37 and 60 is the setup, the registration where we create the verification. The way that I have shown this being working is where the verification setup and the verifier is generated on the client side and sent to the server. There are some other ways of doing this. We could pass the password or the hash of the password to the server and have it generate it. But by doing it this way, what we've done is the server never sees the password at all. This has some implications for how you handle an entire authentication system doing this. If the server never sees the password, this means that there is no chance that you can have a password recovery on the server side. My wife volunteers for Salvation Army, and one of the systems that she uses, you can actually go in and say, reset my password, or even worse, there's another option, show me my password. The fact that the server can actually show the password means that the server doesn't just have the password hash stored, it has the actual unencrypted password stored. And this is a United States government site, so the security is bad on that. Alright, so we've got this number that represents the password. And we've got Q, it's a large pre-chosen prime. The next one, alpha there, is the divisor of P minus 1 into Q in some fashion.